Yeah, thanks, Sayan and Srijan. I thank both of them for giving me this opportunity. So, uh, so first, E0 semi-groups were in the late 1980s. E0 semi-groups were initiated by Powers, and it was developed intensively by Arverson in a series of seminal papers. And an E0 semigroup is basically a one parameter semigroup of endomorphisms on a von Neumann algebra. But mathematically speaking, there is not much reason to restrict our attention to the one-dimensional case. We can equally make the definitions in the multiparameter context. So that's what this talk is about. I will explain a few similarities and I will explain some significant differences. So without, give me a second. Yeah. So, so G is a locally compact second countable Hausdorff topological group, and P is a sub-semi group, which I assume is closed and it contains the identity element. A good example to keep in mind is G is R power D and P is a closed convex cone in R power D. So take for example, G equals R2 and P equals the first quadrant, the closed first quadrant. For technical reasons, we assume that the interior is dense in P. This we need for technical reasons. So let me state the definition of an E0 semigroup. An E0 semigroup over T on B of H is a family. So you have a semigroup of endomorphisms on B of H. So for every X, you have a endomorphism of B of H. B of H is a von Neumann algebra. So it has a sigma weak topology. So you demand that the endomorphism is not just any endomorphism, it is also continuous with respect to that topology. So it's a normal endomorphism and it is also unital. The second property is that alpha x composed with alpha y is alpha xy. This means that the family alpha x is a semigroup. It satisfies the semigroup law. And the third is that it is parameterized by P, and P is a topological space. So there should be some continuity. And the third condition tells you that it is continuous. That means if you take two vectors psi and eta from H and our operator A from BH, the map X going to inner product alpha X A psi eta is continuous. The classical theory of E0 semigroups due to Arveson, Powers, and Zerelson, Lipscher, and many others is the case when G is R and P is the half-line, 0 infinity. Okay? Okay. So, oops, I can't. Yeah. And we are not interested in just studying such family of endomorphisms. We are interested in studying such family of endomorphisms up to an equivalence relation. And the basic equivalence relation in the subject is the following. Suppose alpha is an E0 semigroup on B of H. I perturb alpha by a family of unitaries. So for each x, you pick a unitary ux and perturb alpha x by the formula that I have written. Beta x of A is ux alpha x A ux star. Alpha x is an endomorphism. So if you conjugate it by a unitary ux, that's again going to be an endomorphism. What condition is required to make beta x a semigroup of endomorphism? That is precisely this cocycle condition, which is ux alpha x uy is ux plus 1. So such a thing is called an alpha cocycle. So you take an alpha cocycle and then perturb alpha by beta. We call beta a perturbation of alpha, a cocycle perturbation of alpha. We do not distinguish between alpha and beta. I mean, we do not distinguish between two E0 semigroups if one is a cocycle perturbation of another. So that is the basic equivalence relation in this subject, and we want to understand how E0 semigroups behave under this equivalence relation. And second, if you have an E0 two different Hilbert spaces. Suppose you have one on B of H, another on B of K, then you first bring them together to a common Hilbert space and then compare up to cocycle perturbation. So that is the equivalence of cocycle conjugacy. So that is the equivalence relation. Okay. So I should give an example of an E0 semigroup before going further. So the basic examples are what are called CCR flows and CAR flows, and they come through Fock space construction. So let me explain. So H is a Hilbert space, and gamma H is the symmetric Fock space. So what is a symmetric Fock space? You look at H tensor power n. For every n, you tensor H with H, you tensor H with H with H, 3 times, 4 times, and so on. And you take the symmetric tensors and take the direct sum of such symmetric tensors. That is a symmetric Fock space. This has a special set of vectors called exponential vectors, which is defined as this exponential of u is summation n equals 0 to infinity u tensor n by root n factorial. The reason why root n factorial appears is because of the relation that you want inner product exponential of u times inner product exponential of b is exponential of inner product ub. So because of this relation, you have to put root n factorial. And this is a total set in gamma h, and it is also linearly independent. So in the symmetric Fock space, these exponential vectors form a total set. And there is a collection of unitary operators on the Fock space. So for every vector u in H, there is a unitary operator which is called the Weyl operator of u, w of u, whose action on the exponential vector is given by w of u exponential of v is exponential of minus norm u square by 2 minus uv exponential of u plus v. So these are the Weyl operators, and an important fact is that these Weyl operators generate the Feynman algebra B of gamma h. So on the symmetric Fock space, you have exponential vectors and you have Weyl operators which generates B of gamma h. So here is a first example of here is the first example of a E0 semigroup. So that's a proposition. So suppose you have a strongly continuous semigroup of isometries on H. So you have a, what does that mean? That means that you have a semigroup of isometries. So for every x, Vx is an isometry, and it satisfies the semigroup law, which means that Vx times Vy is Vxy, and it is strongly continuous. Then there is a unique E0 semigroup on the bounded operators on gamma of H, on the symmetric Fock space of H, whose action on the Weyl operators is W of Vxu. So alpha x, W of u is W of Vxu. Because the Weyl operators generate the Feynman algebra B of gamma H, it is enough to specify, the uniqueness is clear. There can be only one such E0 semigroup. Existence is also not very difficult, but I am not going to discuss that. So for every isometric representation, you get an E0 semigroup, which is called the CCR flow. And this E0 semigroup is called the CCR flow associated to the isometric representation V. Okay. Oops. Sorry, I can't move. Yeah, sorry. Just give me a second. Yeah. So in the one parameter case, also I should mention that the CCR flow is based on symmetric Fock space. There is also a corresponding thing on the antisymmetric Fock space, which is called the CAR flow. And it gives that if you have a strongly continuous semigroup of isometries on H, then you get an E0 semigroup on the antisymmetric Fock space, where this equation alpha x w of u is w of vxu. Instead of this, you have creation and annihilation operators. So you have such an E0 semigroup, and that is called the Carr flow or the CAR flow. Okay. In the one parameter case, you have Wooled decomposition, which tells you how any isometric representation looks like. It's basically the standard shift on L2 of 0 infinity. So with multiplicity, and Arvesen's first major theorem is that that multiplicity is a complete invariant for CCR flows. So Arvesen's first major result was that CCR flows in the one parameter case are completely understood. Okay. Yeah. So the first thing that I want to talk about is the similarity between the one parameter theory and the multiparameter theory. I mean, between the one parameter theory and the multiparameter theory. So the basic theory stays true. So what do I mean by that? The basic theory stays intact is the following. We start with an E0 semigroup alpha x, and for each x, look at this set Ex, which is T belongs to B of H, such that alpha x a times T equals Ta for all a in B of H. So you can view alpha x is a endomorphism of B of H. So you can view alpha x as a representation of B of H on H, and you also have the identity representation of B of H on H. And this space is the space of intertwiners between alpha x and the identity representation. And this is a Hilbert space. So the first fact is that if you start with Ex is a Hilbert space. If you take two elements S and T from Ex, and if you look at T star S will intertwine, S intertwines alpha x and identity. So T star S will intertwine identity and identity. So T star S will be in the commutant of identity, identity representation. And the commutant of the identity representation is trivial. So T star S will be a scalar. So this will be a scalar. So this is a well-defined inner product. And with respect to this inner product, Ex is a separable Hilbert space. That's the first thing. So for every X, you have a separable Hilbert space. And look at this bundle of Hilbert spaces. I look at the disjoint union Ex, and this has an associative product structure. So if S is in Ex and T is in Ey, St will be in Exy. So there is a multiplication, X comma S, Y comma T is Xy comma St. It's a fact that if S is in Ex and T is in Ey, St is in Exy. So this multiplication is not just is an associative multiplication, that is clear, because multiplication on B of H is associative. This multiplication is not just any multiplication. It satisfies a very specific property that if you look at the induced map from the tensor product from Ex tensor Ey to Exy, which is S tensor T goes to St, that is a unitary operator. So this bundle of Hilbert spaces, so for every X, you have a Hilbert space, and there is a multiplication on the bundle. And the multiplication is special in the sense that the induced operation from the tensor product is a unitary operator. This is called the product system associated to alpha, and the bundle E alpha together with the product, not just the bundle of Hilbert spaces, also with the product, is called the product system associated to alpha. If you have any bundle of Hilbert spaces as above, so for every X you have a Hilbert space, and you have an associative multiplication rule such that the operation at the level of tensor product is a unitary, then such a thing is called a product system. So for every E0 semigroup, there is a product system. Any bundle of Hilbert spaces which has a multiplicative rule is called a product system. So yeah. So what is the product system of a CCR flow? This can be easily described. So look at an isometric representation of P, that is a semigroup of isometries, and alpha is the CCR flow. Remember that alpha is acting on gamma H. So the product system of alpha can be identified as follows. So the Hilbert space Ex can be identified with the symmetric Fock space of kernel of Dx star. And if you look at the product on the exponential vectors, because exponential vectors are total, it is enough to know what happens on the product of exponential vectors. It is given by exponential of psi times exponential of eta is exponential of psi plus Vx eta for x, y in P and psi in kernel Vx star and eta in kernel Vx star. So this is the product rule. This is the product structure on the, this is the product system associated to the CCR. Okay. Why is the product system important? Because of this theorem due to Arveson. Arveson proved this theorem for P equals for the one-dimensional case, but the same proof goes through in complete generality. So that's what I mean by saying that the basic theory stays intact. So if you have two E0 semigroups, alpha and beta, they are cocycle conjugate if and only if the associated product systems are isomorphic. So the product system associated to the E0 semigroup completely captures all the information about the E0 semigroup that we want. So that's why this product system is a very important invariant in the study of E0 semigroups. Okay. So for every E0 semigroup, there is a product system. So a natural question arises is whether the converse is true. So what is a product system? A product system is a bundle of Hilbert spaces which has a multiplicative structure. So starting with an E0 semigroup, I have given a bundle of Hilbert spaces with a multiplicative structure. So suppose you have a bundle of Hilbert spaces with a multiplicative structure. Does there exist an E0 semigroup whose product system is isomorphic to that? So that is Arveson's question. Suppose E is a product system over P, which means that for every x, Ex is a Hilbert space, and there is a product rule. Ex times Ey goes to Ex plus y, Exy, and the tensor product operation, Ex tensor Ey, S tensor T to St is a unitary. The question is E isomorphic to a product system associated to an E0 semigroup? The answer is not known in complete generality. However, the following are known. If G is R, that is the one-dimensional case, then the answer is yes. This was first proved by Arveson using complicated C-star algebraic techniques. Then later, Steide found a simpler proof. Then later, Arveson himself found a simpler proof. Adapting this proof in a joint work with Murugan, we proved the following thing. This statement, the converse is true. That is, every product system over P is isomorphic to a product system associated to an E0 semigroup if P is a closed convex cone in Rp. For example, if G is Rd and P is the quadrant, if G is R2 and P is the first quadrant, then the converse is true. In fact, you have more. If G is abelian and P has the Archimedean property, then yes. What it means is that there is an order on G which is defined as follows. That is, x is less than or equals y if y minus x belongs to P. So this is the usual order in the one-dimensional case. If G is R and P is 0 infinity, this is the usual order. The Archimedean property means that the following. There exists a such that whatever x that I give, there is a natural number n such that Na is greater than or equals x. If you have in the abelian case with Archimedean property, the answer is true. And A and B are special cases of C. In fact, C is just an incremental generalization of B. The same proof, the proof of B and A, the proof of B is adapted from A. The proof of A and B will work for C also. So this is not a, C is not a, C is just an incremental result. So the question that I want to pose in this talk is, does Arverson's question have an affirmative answer for the following thing? So look at G equals Q plus, that is rationals, positive rationals. So that's a group under multiplication. Look at the natural numbers, n minus 0. I mean, for me, natural numbers always include 0. So I am subtracting n and subtracting 0 from n. So it is the natural numbers 1, 2, 3, etc. So that's a semi-group with multiplication. So will this, is Arverson's question have an affirmative answer for this example? This example will not have the Archimedean property. This is precisely because natural numbers have infinitely many primes. So this is an example where Archimedean property fails. So it would be interesting to know to what extent Arverson's question has an affirmative answer. Okay, so so this is the basic. This is what I meant by saying that the basic theory stays intact. So for every E0 semigroup, there is a product system, and for every product system, there is an E0 semigroup, provided the semigroup is good, like a closed convex cone in RP, or for if it is good, then you have the converse also. Okay, so this forms the first part of my talk. So the second talk, I will focus on some differences. I will illustrate one simple difference. So for the rest of the talk, P will be a closed convex cone in RD. So if for, you can assume that R, you can consider R2 and you can consider the first quadrant if you want. The group is R2 and P is the first quadrant. We assume that P spans RD and P contains no line. So this assumption is just, P spans RD is not an assumption at all, because if P does not span RD, then you take the linear span of P, that will be a subspace of RD, and you work in that subspace. So I can always assume that P spans RD. P contains no line has some, you need that assumption, technical assumption. So in this, I make three statements. The following are some of the differences between the one parameter and the multiparameter theory. The one parameter theory is the case where D equals 1, and the multiparameter theory is the case where D is greater than or equals to. So statement 1, that decomposable product systems need not have a unit. I will not be able to explain that. The statement 2, I will explain. So the opposite of a CCR flow need not be cocycle conjugate to itself. In the one parameter case, it is the opposite of a CCR flow is cocycle conjugate to itself. 3, I mentioned that using the antisymmetric Fock space, you can also construct an E0 semigroup, which is called the CAR flow. In the one parameter case, it is known that CAR flows and CCR flows are one and the same. But this is not true in the multiparameter case, and this is due to Srinivasan of CMI. So these are some of the differences. I will illustrate the second difference in my talk, in the rest of the talk. So what do I mean by opposite of a CCR flow? Okay, what is an opposite of an E0 semigroup? So alpha is an E0 semigroup. I look at its product system. So EX is the space of intertwiners. I look at the disjoint union. The disjoint union is E. That is set of all x comma t, where x is in P and t is in EX. That is the product system of alpha. We have a product rule. X comma s, y comma t is Here, the semigroup is a closed convex cone. So the semigroup operation is addition, not multiplication. So it's x plus y comma st. So this defines the product on the product system. So that is the product system associated to alpha. I'm going to define a new product rule by flipping T and S. So define a new product rule on E as x comma s, y comma t is x plus y ts. In the previous line, you have st, now you have ts. This product is, you are just flipping the product, so it is the opposite. So this is again E is again a bundle of Hilbert spaces, and you have a product. So that is a product system. This product system, I call it as E opposite. We call E opposite the opposite of the product system. Okay. So here is a little bit of jargon. If E is isomorphic to E opposite, I call the product system symmetric. Otherwise, we call it asymmetric. In the one-dimensional case, what do we know? In the one-dimensional case means P equals the half line. We have the following. So the one-parameter CCR flows are symmetric. So if you take a CCR flow, if it is one parameter, then its opposite is isomorphic to itself. This is because Arveson has a complete classification of type 1 E0 semigroups, something called type 1 E0 semigroups, and they are basically CCR flows. Opposite of a type 1 E0 semigroup is again type 1. So it follows from the classification due to Arveson. Of course, there are, even in the one parameter case, there are asymmetric E0 semigroups. This is due to Cyril Sun, and he completely came out of left field to construct these E0 semigroups using his probabilistic approach. So Cyril Sun's approach to E0 semigroup is via probability, and that is, he constructed many examples of E0, non-trivial E0 semigroups in the one parameter case using probability theory. So what I want to say, what I want to discuss is that in the multiparameter context, asymmetry is observed even with CCR flows. Even CCR flows fails to be symmetric. That is somewhat disconcerting at present, but it is not so much because if you the isometric representations, the multiparameter isometric representations are complicated itself. The one parameter isometric representation has a simple description due to Wool decomposition, but in the multiparameter case, you don't have such a thing. So that's why asymmetry is observed even with CCR flows. So, okay. The first theorem is that the opposite of a CCR flow is a CCR flow. So, so how do we prove this? Let me give a sketch of the proof. So we start with an isometric representation of P on H. So it's an isometric representation of P. So you can always dilate that to a unitary representation. What I mean by that is that you can put the Hilbert space H in a bigger Hilbert space H tilde, and you have a unitary representation of the group RB such that B is the compression of U on H. So H tilde contains H, and V is the compression of U on H. So this way you can always dilate it, but you dilate it in a minimal fashion. What do I mean by a minimal fashion? Suppose H tilde is a minimal unitary dilation, which means that suppose there is another dilation K, then H tilde embeds inside K. That's what I mean by saying that it's a minimal dilation. So you dilate V in a minimal fashion to a unitary representation on H tilde. Then okay, so V is the compression of that's the first step. V is the compression of U. So V is the compression of U on H. So H is invariant under QA. That's so its ortho complement will be invariant under its conjugates, UA star. So that is U minus A because U is a unitary representation. So its ortho complement is invariant under WA. Now WA, you restrict WA, you restrict U minus A to HA and call it as WA. Now WA is an isometric representation of P on K. Because U is a semigroup of isometries, semigroup of unitaries, W is a semigroup of isometries on K. Now it is with this, it is very easy to exhibit isomorphism between the product system. So remember the product systems of the CCR flow. I look at the CCR flow associated to W. So the product system is the symmetric Fock space of kernel of WA star. Look at the product system associated to the CCR flow associated to V, that is gamma of kernel of VA star. So there is a map from the left hand side to the right hand side, which takes exponential of psi to exponential of UA psi. You can verify that this map is well defined, and this provides an isomorphism between the CCR flow alpha W and the opposite of alpha V. Alpha W is the CCR flow associated to W. Alpha V is the CCR flow associated to V. This map provides an isomorphism between the product system associated to alpha W and the opposite of the product system associated to alpha V. Therefore, the opposite of a CCR flow is a CCR flow, and the opposite is the CCR flow associated to W, and I call W V opposite. Okay. So this is the idea of the proof, and I would like to make a comment here. So I do not know whether one can, in the statement of the theorem, whether one can replace CCR with CAR. So it's I do not know whether the opposite of a CAR flow is a CAR flow or not. This proof will break down for CAR. So it's a question that whether the opposite of a CAR flow is a CAR flow is a question. Okay. So when is a CCR flow symmetric? When is the CCR flow symmetric means when is it cocycle conjugate to its opposite? You know that the opposite of alpha V is alpha V opposite. Alpha V is the CCR flow associated to V. The opposite of alpha V is alpha V opposite. So alpha V is symmetric if and only if the two representations V and V opposite are unitarily equivalent. It is clear that 2 implies 1, because if V and V opposite are unitarily equivalent, then alpha V and alpha V opposite are unitarily equivalent. But on the other hand, if alpha V and alpha V opposite are cocycle conjugate, then V and V opposite are unitarily equivalent. This is because the CCR flow remembers the equivalence class of V. This is another. The reason is another theorem. This is proved by myself and independently by Srinivasan in the higher dimensional case. But the proof is really the difficult part is really is proving in the one parameter case, which was proved first by Arvasan. The difficult part really lies in proving the statement for the one parameter case, and that means the reason in the one parameter case, and that is due to Arvasan. So a CCR flow is symmetric if and only if V and V opposite are unitarily equal. Now, so to exhibit a asymmetric CCR flow, all I have to exhibit is an isometric representation V, which is not unitarily equivalent to V opposite. So here is a class of examples. So you look at a subset of RP. I call that as a P space if that set is closed, non-empty, and proper. It's not the whole space RP. Okay, proper means not equal to RP. So it's a non-empty, proper, closed set, and it is invariant under P. That is, if I take an X in P and if I translate A by X, you get A again. Actually, it's contained in A, but one can prove easily that A plus X has to be equal to A. So if you translate A by P, you get A. So because A is invariant under translation, if you look at the Hilbert space L2 of A, the cone will act as isometries on L2A by translations. Because A is invariant under shift, L2A, you get shifts for each element X in P, you get a shift operator Vx on L2A, and that gives rise to an isometric representation. That isometric representation, I call it as VA, and I call the associated CCR flow alpha A. Okay. So what are some examples of some examples? You can take A equals P itself, or you can take P union P plus A and things like that. Yeah. So here is the final theorem. For a P space, the following are equivalent. The CCR flow alpha A is symmetric, which means the isometric representation VA and VA opposite. That happens only if minus A and interior A complement or translates of each other. So this is because VA opposite is the isometric representation associated to minus interior of A complement. So that's why this happens. And so to give examples of asymmetric CCR flows, I can simply take A equals P. If I take A equals P, minus P will not be a translate of interior of P complement. So if I take A equals P, we get an asymmetric CCR flow. If I take a half space like set of all X in RD such that lambda X is greater than or equal 0, for lambda in P star, we get symmetric CCR flows. So in the multiparameter case, you get both symmetric and asymmetric CCR flows. As far as car flows are concerned, the car flow associated to A equals P is also asymmetric, but it is not clear whether the opposite of a car flow is a car flow. You can exhibit a car flow which is asymmetric, but it is not clear whether the opposite of a car flow is a car flow. So I think I finished quite early. So thanks. I'm sorry I finished quite early.
No problem. Thank you very much. Yeah. So are there any questions, comments?
Yeah, okay. This is Raja here.
Yeah.
So some CCR flows are isomorphic to some CCR flows there in RD.
Yeah, that is true. If you take a half space, that is due to Anbu has recently had a paper. So if you take the half space, A equals X belongs to RD, lambda X greater than or equals 0, the last set A, the CCR flow associated to the half space A would be isomorphic to the CAR flow associated to half space. So,
okay.
Yeah.
Okay, thank you.
Yeah, thank you. Thank you. You're welcome.
A very nice talk, Sundar.
Yeah, thank you. Nice
I put a trivial question in the chat. Do you make sure that the isometries are not onto?
Yeah, it is not onto. If it is onto, then you get unitary representations, and it's a pure isometric representation.
Yes. So well, I sort of wanted that to be emphasized somewhere. Okay.
Yeah.
Okay, that was one point. Secondly, there are 4 papers by Arveson. Which one do you take as basic to recommend to people?
All four continuous analogs of Fox space.
Yeah, because
From one, the first paper is the most important paper.
yes, that is true. And the second one has nice example, that is after 5 or 6 pages.
Yeah, yeah.
But you recommend the first one, that is good.
No,
Okay,
all four are important, but
yes, that
one
is
has to
true.
start
But
with one.
yeah, I just wanted. I mean, I read them in early 90s, 80s when they came. I was in Chandigarh then.
Okay.
Great. Thank you. Very nice talk.
Thank you.
So are there more questions, comments? Okay, I don't see any. So I have a very naive question. Can the theory of semigroup C-star algebras be connected to this theory of E0 semigroups or something?
Yeah, they are intricately connected because isometric representations appear in semigroup C-star algebras also. So they are intricate. I mean, they are connected in some sense. But for example, in the last theorem that for a P space, the following are equivalent. The CCR flow alpha A is symmetric. The proof of this requires semigroup C-star algebras. Maybe I should have spent 2-3 more slides on this. I thought this itself will take 1 hour, but I should have been careful. Yeah, this theorem 1 and 2, 1 implies 2, requires semigroup C-star algebras.
Okay, that's interesting.
Yeah, so.
I could ask a question. You confine your attention to commutative semigroups all the time? Or do you have analogs of product systems for non-commutative semigroups also now?
You can define product systems for non-commutative semigroups, but whether every product system is isomorphic to a E0 semigroup, that is not clear.
Oh, I see. Okay. And does amenability help?
These questions are not clear. They are not known yet. Yeah.
Okay. Thank you.